Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on frequency modulation. Okay, so for this video, I'm going to share with you firstly, okay, what is actually a Bessel function table. Okay, so how does the Bessel function table look like in a figure? I'm also going to share with you how can we actually make use of the Bessel function table. Last but not least, on the last part of this video, okay, I'm going to have an example. Okay, how can we actually find the number of sets of significant side frequency and also the bandwidth of frequency modulated signal using Bessel function table. So basically, these are all the objective of this video. This will be the part 4 series discussion on frequency modulation. So guys, if you're keen to know more about frequency modulation, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on frequency modulation. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are also welcome to ask me your question through the comment. Before I continue, okay, I'd like to urge you guys to help this channel by pressing the like button. Okay, when more you guys actually help me to press the like button, this video will have a better chances to reach out to a larger audience. So guys, give me a few seconds. Help me by pressing the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Firstly, let's quickly understand what is actually a Bessel function. Okay, so in simple word, Bessel function is just a mathematical tools that will be helping us to solve the frequency modulated signal. On my earlier on discussion on frequency modulation, I have actually proved that the equation of the frequency modulated signal can be governed by this equation. Okay, so this equation can be further expanded as is shown over here. Okay, so what are all these? So for example, this JNMF, okay, so this MF is actually the modulation index. Okay, so this term here, this term here, this term here, they are actually called the Bessel function coefficient. Okay, so these are all the Bessel function coefficient. Later on, I'm going to show it to you how can we actually make use of this, okay, to compute some of the outcome that we actually want. Okay, so from this equation, you can see that the FM actually has an infinite number of frequency component on both sides of the carrier frequency. Okay, so what does this mean? Okay, so this is very obvious. This is actually the location of the carrier frequency. So on the next significant one, you can see that this is actually on the left-hand side of the carrier frequency. This is actually on the right-hand side of the carrier frequency. So on the next equation, okay, you can see that this is further away. This is 2 FM away from the carrier frequency. Okay, so again, this will be on the left-hand side. Okay, so this will be 2 times FM, okay, away from the carrier frequency. This is on the right-hand side. And this thing go on and on. And from this equation here, you can see that they actually has infinite number of frequency component on both sides of the carrier frequency. Okay, but in the practical sense, okay, so we don't need to send so much. So basically, the first objective, we need to know the number of sets of frequency that is actually significant. So for example, if this is the significant, we will just cut over here. The rest we will just omit. Okay, so basically the first objective is how to find the number of sets of significant frequency. So basically this is the meaning here. Okay, as you can see from here, this equation go on and on and on, and they have infinite number of frequency component. So later on you will see how am I going to find this number of sets of significant frequency. Okay, so next. Okay, the frequency value of this side frequency, they are all integer, okay, which means that this is a whole number, no so-called decimal, okay, multiply of the modulating signal frequency away from the carrier frequency and are actually given by this equation here. Okay, plus minus, which means that on the left-hand side and also on the right-hand side, okay, where n is the order of the side frequency. Okay, so let's take a look on this picture. Okay, so this is actually the location of the carrier frequency. Okay, as I mentioned earlier on, okay, based on the graph that is actually over here, you can see that this FC minus FM, which is over here, okay, so this is actually friend on the left-hand side. This part here is actually friend on the right-hand side. As for the second part of the equation here, you can see that they actually further away, 2 times FM away from the carrier frequency. Okay, so again, 2 times FM away from the carrier frequency, you can actually see this over here. So actually earlier on, I did mention that this is actually called the Bessel function coefficient. Okay, so the peak amplitude of this side frequency basically are given by this equation. Okay, so this is a EC, okay, multiplied by the Bessel function coefficient. This will give the peak value. Okay, so this is what we call the amplitude spectrum. Okay, so on my example, okay, I will show it to you how can we actually plot this amplitude spectrum. Okay, so let's move on. Okay, so this is the so-called the diagram that I showed it to you earlier on. So this is the Bessel function table. Okay, so these are all the Bessel function coefficient that I mentioned earlier on. This together with the EC will give us the peak value. Okay, so what is this? Okay, so on this column here, okay, you can see that this is what we call the modulation index. Okay, so we must know this modulation index before we can make use of this Bessel function table. Okay, so again, all this with an example will be more clear. So for a carrier that is actually modulated by a single sine wave, okay, which means that if you do a frequency modulated signal, the modulating signal, let's say, is a single sine wave, okay, so basically the resulting frequency spectrum can be calculated using Bessel function of the first kind, okay, as a function of the sideband numbers and the modulation index. Okay, the carrier and sideband amplitude are illustrated for different modulation index of FM signal. Okay, the sideband produced by FM are actually governed by the Bessel function of the first kind and also the n order, which is actually denoted as is shown over here, JNX, okay, where X is the modulation index. The Bessel function determine the magnitudes and also the sign of the frequency component in the FM spectrum. Okay, so this function resemble like a damped sine wave. Okay, so I'm going to explain all these, okay, part by part. Okay, so basically from this diagram here, okay, so basically this is actually the Bessel function. Okay, how you draw all this so-called curve. Okay, so for example, this is the general form. Okay, so under the general form, let's say, let's draw the first one, which is the J0, okay, X here. So you just need to substitute the n equals to 0 into this equation, and you actually have this outcome. And if you increase the X value, then you will be able to draw the blue color as is shown over here. Okay, I think if you draw this in MATLAB, I think will be much more easier, okay, rather by the manual way. So on the second one, let's say this is J1X, okay, which is the green color. Okay, so what you need to do is basically you just substitute the n equals to 1 onto this equation. Then you actually have this equation. And again, if you increase your x value, then you will be able to plot the curve in green. And this thing can continue on and on for the 2, 3, 4, and 5. Okay, so but let's not dwell so much, okay, on how we actually plot this graph. Okay, so most important, how can we actually make use of this graph, okay, to obtain the Bessel function table? That's all. That's all we need. Okay, so let's come to the key important point that we actually have from this graph here. So the J0X can actually decide the amplitude of the carrier. Okay, so basically from here, you can see that this part here actually will decide the amplitude of the carrier. So this is what it means. The J1X actually control the first upper and lower sideband. Okay, so the first one is actually at n equals to 2. So from here, you can see that the first one, okay, so basically, which is the first one, which is in green, they will be the one that control the first upper and the lower sideband. And JNX actually govern the amplitude of the n upper and lower sideband. Okay, so let's say, okay, at n equals to 3, okay, you can see that this number 2 will be the one that control. And when n equals to 4, okay, so over here, you can see that the number 3 one is the one that actually control. So this is the meaning here. Okay, so the JNX actually govern the amplitude of the n upper and lower sideband. okay, the higher the order, the Bessel function actually start from 0, okay, which means that the first one will be the one that start from 1. The rest of them, which is the higher order Bessel function, all of them actually start from 0. So this is what it means. The higher order Bessel function start from 0, which means that the only one, okay, which is the 0, 1 will appear at 1. The rest will be all start from 0. And more gradually, so higher order sideband only have significant energy when X is large. Okay, so what does this mean? Okay, let's take an example here. Let's say the example of this uh green color line, which is 3. You can see that at the higher order, okay, they become more significant. Okay, as you can see from here, they become more significant. So this is what it means. Okay, so it means that the higher order sideband, okay, they will only have significant energy when the X is actually large. Okay, the spectrum bandwidth actually increase with X, which means that the higher the X, okay, the larger the bandwidth that you actually need to send a signal. Okay, so the upper and lower sideband actually grow towards higher and lower frequency, which means that if you look at the frequency spectrum, okay, when you actually has a bigger X, okay, which means that they go further right and also further left, okay, so respectively. Okay, so as X increase, the energy of the sideband very much like a damped sinusoidal, as you can see from this graph here. Let's say for this green one, you can see that it's actually like a damped sine wave. Okay, so basically these are the key thing that you actually use to describe this graph here. Okay, since the sideband appeared on both sides of the carrier, okay, so early on I have mentioned that they actually appear on the both sides of the carrier, so therefore their count is double. Okay, so I will illustrate this again. So which means that we need to double the effect and then multiply by the modulating frequency, okay, to determine the bandwidth. Okay, so what does this mean? This means that the bandwidth is actually first one will be double, okay, which is illustrated here. So this will be the double 2 times because it's double. We multiply by the number of set of significant frequency and then multiply by the modulating frequency as illustrated here. Okay, since the sideband appear on both sides of the carrier, which is the double, and then we need to multiply the modulating frequency, okay, in order to determine the bandwidth. Let me give you an example. Okay, for example, okay, we have this frequency deviation of 3 kilohertz, and they are actually modulated by a 2.2 kilohertz audio tone result in a modulation index of 1.36. Okay, so this is the frequency deviation. This is actually the modulating signal. How we compute the modulation index? Okay, so modulation index is equals to frequency deviation over the frequency of the modulating signal. Okay, so basically in short, the modulation index is equals to 3 over 2.2, which we will be able to obtain 1.36. So this is how we obtain the modulation index. It's actually the frequency deviation over the modulating signal. Suppose we limit ourselves to only those sideband with a relative amplitude of at least 0.01. Okay, so how can we actually examine the charge of this Bessel function table? Okay, so earlier on I have computed that the modulation index is actually 1.36. So this so-called this column here, which is the modulation index, if you take a look over here, 1.36 is in between 1 and 1.5, right? So it's actually in between here. So basically, as I mentioned earlier on, okay, we only consider anything that is bigger than 0.01. And from here, you can see that at 1.5 is already 0.01. So therefore, from here, I can compute that this is the so-called significant number of sets is actually equals to 3, J3. Okay, so this is the n. So therefore, I know that n is equals to 3. Okay, so basically, this is what I mean. Examining the charge, okay, we show that this modulation index produce 3 sideband. Okay, as I mentioned earlier on, this one I can ignore because 1.36 is actually in between here. So therefore, I'm quite confident to say that this 0.02, okay, on this part here will be significant. And if I take a close look here, the n order is equals to 3. And therefore, I know that the significant side frequency is actually 3, which means that this n is equals to 3. Okay, so when double, okay, these 3 sideband give us this equation. So this is the double effect. This is the number of set of significant frequency, and this is the modulating frequency. So therefore, they actually give us a bandwidth of 13.2 kilohertz. Okay, so don't worry. Later on, I'll have another example to compute this. But over here, you can see that, okay, firstly, I need to know the so-called the significant, okay, the side frequency that is actually important. Okay, this will give us the n value, and from here, you can easily compute the bandwidth. Okay, so this is actually what we have discussed earlier on, but I like to go a little bit in depth to discuss on this graph here. Okay, for example, okay, when we actually say that the modulation index is actually equals to 1. Okay, so basically I replace this with a so-called dash line over here. Okay, you can see that these are significant. Okay, so you can see that this is significant, this is significant, this is significant, this is significant. The rest is actually under 0.01, for example, here. So I actually will have 1, 2, 3, 4 dot on the modulation index equals to 1. So next, okay, let me do the modulation index equals to 2. Okay, so this is the modulation index equals to 2. So from here, again, you can see that I have 1, 2, 3, 4, 5. The rest is actually less than 0.01, which I will so-called omit. Okay, so basically, this is for MF equals to 1, which I have 1, 2, 3, 4, and MF equals to 2, I actually have 1, 2, 3, 4, 5. Okay, so what does all this so-called tells me? Okay, let's take a look on this Bessel function table again. Okay, so basically, remember, okay, when I mentioned that, okay, the modulation index equals to 1, I have also mentioned that the modulation index equals to 2. Okay, earlier on, if you still remember, okay, under this modulation index 1, I actually have 1, 2, 3, 4, 4 significant points on the graph. As for the modulation index 2, I actually have 1, 2, 3, 4, 5 significant points, okay, on the graph. Okay, let's take a closer look. Okay, so this is what I have shown it to you earlier on. Okay, I put all this together so that it will be much easier to explain here. So as I mentioned earlier on this modulation index, I actually have this 1, 2, 3, 4. Okay, you can see that this is actually the 0.77, which is here. This is around 0.77. Okay, the next one is 0.44. The next one over here, which is 0.44. Okay, next one is 0.11, okay, which is around here, which is 0.11. And last but not least, which is 0.02, which is around here, which is around 0.02. So this is for the modulation index 1. Okay, as for modulation index 2, okay, so you need to be very careful, okay, because the first one is actually on the blue line, which is here. So this part, okay, is actually about 0.22, which is shown over here. So the second one is actually the green line, okay, which is around 0.58, which is illustrated here. So the second, which is the 2 here, which is the purple red color line here. So this will be the third one, okay, which is around the 0.35 values. And this thing go on and on. So basically from here, you can see that the number of set that is actually significant. You can see from here, anything that is less than 0.01, I will ignore. So from here, you actually can obtain so-called the number of set of significant frequency that you actually want to contribute to the calculation of the bandwidth of the frequency modulated signal. Okay, so before I go through the example, okay, if you have learned something from this video, okay, please help me by like this video. And again, for those who are new to this channel, and again, I will appreciate if you have learned something from this video, okay, please consider to subscribe and turn on your notification bell. Okay, let's take a look on the example so that it will be very clear. Okay, so for an FM modulated, okay, where the modulation index is equals to 1, okay, a modulating signal, okay, basically this is the modulating signal, and we have this carrier signal over here. Okay, so firstly, okay, we are tasked to determine the number of set of significant side frequency. Okay, so how can we actually do this? Okay, so if you remember over here, you actually can see that this is actually the modulation index. Okay, if you still remember the whole chart of the Bessel function table, I just trim it. Okay, so but over here, this column actually will indicate the modulation index. Okay, so since the modulation index is equals to 1, okay, so I do it, this equals to 1, and I move the most significant all the way to the right, and I can see that the number of set of significant side frequency is equals to 3. Can you see here? J3. So therefore, I know that my n is equals to 3. Okay, so this is how I find the number of set of significant side frequency. Once I have the modulation index, I look into the Bessel function table. Okay, so one, I will move all the way to the right until there's no more number. Then I move it up, and this will tells me the number of sets of significant side frequency, which is 3. Part 2, how to find the bandwidth. Okay, so if you still remember how to find the bandwidth will be 2 times n times fm. Okay, so this is actually the so-called double. Okay, since the thing exists on the both sides, so we need to multiply by 2. This is the number of set of significant side frequency. This is the frequency of the modulating signal. So it's actually 2 times 3. So how to obtain the so-called modulating frequency, which is here, 1K. Okay, so therefore we can compute that the bandwidth is equal to 6 kilohertz. Okay, so next we are tasked to draw the amplitude spectrum. Okay, so how can we actually draw the frequency amplitude spectrum here? Okay, so this is the Bessel function table when the modulation index is equal to 1. Okay, so basically we actually have this number, okay, 0.77, 0.44, 0.11, and 0.02. So this is actually how we actually obtain. So we just copy so-called this Bessel significant onto this chart here. Next, okay, so what we are going to do is we will concentrate on the frequency. Okay, so we are going to concentrate on the frequency. This is actually the carrier frequency. If you still remember, the carrier frequency is 500 kilohertz, and the modulating signal is equal to 1 kilohertz. So in short, this will be 500 kilohertz. So they will be on the left, which is 499 and 501. Okay, so basically this is how we compute here. So on the left and on the right, and again, 2 times away, okay, on 2 FM away from the carrier, and this will be on the other side. And if you still remember, we just need to compute all the way to the n equals to 3. Okay, so basically this will be the amplitude spectrum. Okay, so this is the center part. Okay, so this is actually space 1 FM, okay, on the left and also on the right. Okay, so this will be the amplitude. I will show it to you how we can compute this. This will be on another part here. Okay, so which is governed by this set of equation, and the last part which is by this set of equation. So I hope it's clear how I actually obtain all this. Okay, how to obtain the so-called the amplitude, okay, from here. Okay, so I will show it to you. Okay, so how to obtain this? For example, okay, we obtain that the EC is actually equals to 10 volt. Okay, so basically this is given in the question. If you still remember this EC, okay, so basically is equals to 10 from here. Okay, so basically if this is equals to 10, what I need to do is basically I will multiply this 0.77 by 10, which give me 7.7. So I know that the amplitude here is 7.7. And this is 0.44. I'll multiply by 10. I will actually get this 4.4. Okay, so this will be 4.4. And again, this is 0.11. I'll multiply by 10, which will give me 1.1. And last but not least, 0.02 multiplied by 10, which will give me 0.2 here. So basically with this, you can see that I have successfully plot the amplitude spectrum. Okay, just a few comments before I end this video. Okay, so one thing I want to so-called want you guys to take note that this is actually symmetric. Okay, so basically this is the center point. Okay, you can see that everything on the left will also appear exactly on the right. Okay, so whatever is on the left, you will actually see on the right. And how you get all the amplitude value is from here. So basically the first one, okay, will be at the carrier. Okay, so the carrier is 500. Okay, so the first one will be at 7.6, 7.7. Okay, the next one will be having the frequency at 499 and 501, which is shown over here, 499 and 501, and the amplitude value is actually 4.4. Same for this, the second pair, which is 498 and 502. As you can see from here, okay, the amplitude is actually 1.1. And last but not least, okay, on the third pair, which I think will be, you will be able to understand by now. Okay, so basically the key thing that you learn from this video is, firstly, how to obtain the number of significant frequency, okay, from the Bessel function table. And then after from there, you will be able to compute the bandwidth, which is the 2 times n times fm. And last but not least, I also show this example, how can we actually plot the amplitude spectrum of a frequency modulated signal. Okay, so with this, I'd like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.